this is APAB Calc. We are doing the second video in section 1.4, talking about continuity. So we're going to talk about a couple of functions that are always continuous, how to spot functions that have discontinuities, and then just some basic properties of continuous functions that you can find on page 75 of your textbook. I will say that continuity is usually pretty intuitive. Okay, so a couple things. Functions that are nice and happy and always continuous. Polynomials are like the well-adjusted children of the function world. They have no issues, they have no asymptotes, no jumps, they are happy and easy to deal with. So things like, for instance, x squared, or x plus 7, or x cubed minus 2.3x plus 4, right? Those are all polynomials, all continuous. Or just the number 7, right? That's a polynomial. It happens to be a monomial that is a constant. Sine and cosine are also both always happy continuous functions. So some big hints about how to spot a discontinuity, and we talked about this a little bit at the end of the last video. If you have a denominator, and if that denominator can equal 0, you're going to have a discontinuity. So the example we did in the last one, I think at one point we talked about 1 over x, and how if x equals 0, there's a vertical asymptote. That's a discontinuity, right? And also piecewise functions, which we're going to talk about specifically in this video, where the pieces don't connect, and I'll show you what I mean by that in a minute. So before we go on to that, I did want to just walk through a couple properties of continuous functions. If you put a number in front of a continuous function, so let's say f of x and g of x are continuous at some x equals c, then any of these things are also going to be continuous at c. Let me walk you through it. Some constant times a function is going to be continuous. Perfect example, I told you x squared is always continuous. If you put a 10 in front of that and make it 10x squared, it is still always continuous. If you have two continuous functions and you add them or subtract them, you're still going to get a continuous function. Well, this polynomial is a perfect example of that, because each one of these three pieces is continuous, right? X cubed is a polynomial, it's continuous. The 2.3x is a continuous function, and the 4 is continuous, and if you add or subtract them, they're also going to yield a continuous function. The product of continuous functions is continuous. So if you multiply x squared times sine of x, well, x squared is continuous, and so is sine, so boom, continuous. And division of continuous functions is continuous, except for the time when the denominator equals 0, which we talked about, right? So if f and g are continuous, they will be continuous at c unless this function happens to be 0 at c, right? You can't have a 0 on the bottom. So just a couple properties of continuity. So let's walk through. All right. So when we talk about piecewise functions, and I say that they are not continuous if they don't connect, let me show you what I mean by that. So this will be our example 2. Technically in this section, okay? So we're going to describe the continuity the same way that we've been doing, okay? So I'm going to give you f of x equals x plus 1 for x values less than negative 1, and x squared minus 1 for x values from negative 1 to 2, and 5x for x values greater than or equal to 2. Okay, so the way a piecewise function works is there's some function rule that you're supposed to use, and then there's some domain restriction that tells you when to use it, right? And I realize that this is probably a thing that you totally hated in Algebra 2, and here we are again with the piecewise functions. But when you have a piecewise function, basically what this is telling you is that you're going to use this line for this graph, for this f of x, but only for x values less than negative 1, meaning to the left of negative 1. And then you're going to use this parabola for the graph, but only for values from negative 1 to 2, right? And so you're going to have a little chunk of a parabola in the middle of this graph, and then for x values bigger than or equal to 2, you're going to use the 5x. So when we talk about these things not connecting, the trick is that each one of these pieces, and I'm going to go ahead and call these 1, 2, and 3, okay? What I want you to notice is that the first piece is continuous always, okay? So if I asked you, so see how each one of these happens to be a polynomial, right? They're all polynomials. So each one of these pieces is a nice, happy, continuous function. The question is, do they run into each other? So I have to look at these spots where we switch. So if any of you ever have done track and run any of the relay events, you know that the trickiest part of a relay event is when you switch the baton, right? That's when you risk dropping the baton and something goes wrong. The same thing's true if you work at a job and you have a shift change, right? If the person who's taken over for you doesn't arrive on time, then you might get stuck working late, right? So the trickiest issue is making sure everybody's there on time. So I have these two things. Now what I do is I call these breakpoints, okay? This is a Hoganism. Right, this is a Hoganism. I call these breakpoints, okay? And they are the point where you switch from one function to the other. So, at x equals -1, I'm switching from the first function to the second function, right? That's when, so up until -1, I use the first function, but starting at -1, I switch to the second function. And at x equals 2, I'm switching, that's not how you spell switch, from the second function to the third function, right? So those are my two breakpoints. So the only places that this thing could have a discontinuity are at those breakpoints because I don't know if the two graphs run into each other. I know each one of these pieces is nice and happy and continuous for its own little piece of graph. The question is, do they run into each other? So the calculus way to answer this, ignore that. The calculus way to answer this is to look at limits. So if I want the limit as x approaches -1 from the left of this function, right? These are the values left of -1. So I would plug into this function and get -1 plus 1, which is 0. If I wanted to approach -1 from the right of this function, I would plug in to this function, right? So this was function number 1 because I used number 1 to the left of -1. This will be function number 2. Well, that'll be a -1 squared minus a 1, which is a 1 minus 1 and is also a 0. So because they're both zeros, this thing is continuous at that x equals -1. The two graphs run into each other. At x equals 2, right? When I look at x equals 2, I'm going to do the same thing. I'm going to look at how the graph behaves on the left side, right? So the limit as x approaches 2 from the left of this function, and the limit as x approaches 2 from the right of this function. So 2 from the left is going to use this function number 2, which is going to be 2 squared minus 1, and that's a 3. 2 from the right is going to use the third function, function 3, right? Which is 5 times 2, and that's a 10. Since 3 is not equal to 10, this limit doesn't exist, and we have a jump discontinuity. So a jump, which is called non-removable, right? That's a type of non-removable discontinuity at x equals 2. Okay? Now, if you wanted to look at what these graphs look like to get a visual of it, you certainly can graph a piecewise function. Graphing piecewise functions is something that we are routinely asked to do in Algebra 2 just to make sure you know how. But honestly, once you get past Algebra 2, it's not really worth your time to hand graph a piecewise function. If you stubbornly, really wanted to, right? -1, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. That'll do it. Okay. So what I know is I have a y value of up to -1, so we're here. Okay, so this first graph would look like this. If I were graphing this first graph would look like this, right? So that's x plus 1, and it has an open circle at -1 because that's not equal to. And then the second graph would look like this. It would be a parabola like this, with closed dots because those, this one's an open dot because that doesn't say equal to, okay? And so that would be my second graph, right? This would be x squared minus 1. And then my 5x would be my last graph, and it would start here and do something like this, right? So that'd be 5x. So what I want you to notice is that the orange graph runs into, right, this orange graph runs into the aqua-colored graph, and there is not a discontinuity there. But at x equals 2, there is a jump discontinuity, right? You can see that there's a jump right here. Now, again, I wouldn't recommend graphing a piecewise function by hand. The easiest way to evaluate a piecewise function is to just look at the individual pieces, right? Look at the individual pieces of the function, see if the pieces are continuous, and then look at those breakpoints where they run into each other. So we're going to do a P2 in just a sec. That's basically exactly the same as this. Again, you're going to describe the continuity of the function. So, oh, sorry, I should mention, so I would say this, and I would say continuous for all other x. Right? Okay, so, cool. Moving on. So if we do a P2, where we describe the continuity, so P2, describe the continuity. Let's do g of x equals, let's do, sine x for values less than or equal to 0. We'll do we'll do 2x plus 3 from 0 to 2, and we'll do cosine of pi x, because I figure I'll be a jerk and give you some trig. All right, cool. Okay, so go ahead and give it a try. Pause me if you want. Okay, so first thing I notice is that all of these are continuous functions, right? So I'm going to just call these 1, 2, and 3 so I can make my point, okay? Each one of these is continuous, right? They're all either a sine, a cosine, or a polynomial, so they're all continuous, right? They're not an issue. So really, all I have to do is check these breakpoints, right? So my breakpoints are at 0 and 2, right? So breakpoints, and again, that's a Hoganism, right? So my breakpoints are at x is 0 and 2. So those are the two spots that I have to check for discontinuities, right? So at x equals 0, the limit as x approaches 0 from the left of this function g of x is going to use the values before 0, so that's going to be sine of 0, which is 0. And if you're like, oh, how does she know the sine of 0 is 0? You need to memorize your unit circle. I have tons of good videos on that if you look in the pre-calc section of my website, if you look on the pre-calc stuff on my website and also on my YouTube channel. So when I check 0 on the other side, I'm going to get 2 times 0 plus 3, which is a 3. Well, since 0 is not equal to 3, right, that's a bad way to write that. Let's say 0 is not equal to 3. We have a jump discontinuity at x equals 0, right? Now let's try 2. So at 2, right, so notice that here I used 0 when I switched from 1 to 2, right? So I used function 1 and then I used function 2, right? Well, at x equals 2, I'm switching from function 2 to function 3, right? So my left-sided limit is going to be function 2. So the limit as I approach 2 from the left of g of x is going to be 2 times 2 plus 3, which is 7. The limit, and so again, notice that I used, here I used function 2, right? And then the limit as x approaches 2 from the right of g of x is going to be 7 times the cosine of 2 pi, right? And that's a 7 times a 1, right? So that's a 7. Since they're the same number, right, the answer is that I'm continuous at x equals 2. So when I'm asked to describe the continuity, I would say g of x is continuous for all x except there's a non-removable discontinuity, which in this case, if you want to say happens to be a jump, at x equals 0, right? And if you were to graph these pieces, you would see that that's exactly what happens, that there's this jump. Again, up to you if you chose to graph it or not, right? If you chose to graph this, 1, 2, 3, 4, 5, 6, 7, 1, 2. Okay, so if you chose to graph this, sine is a little bit tricky because if you're going by ones, that's tricky. But sine's gonna look something like this. Let's see, if it was a 1 lands me partly in quadrant 1, so it's gonna look something like this. Okay, and then this guy is gonna start at 3, 1, 2, 3, with an open circle and go kind of like this, right? and sorry, he's also an open circle. And then the cosine is going to pick up and kind of go like this, like forever, up and down, and it's a terrible graph, but you get the gist. So the idea is that this spot fills the same hole, so see how there's a jump at 0, but a continuity and continuous at x equals 2. So this is a terrible version of that graph, but you kind of get the gist. Again, not worth graphing piecewise functions by hand. That's a terrible life choice. Okay, cool. Let's stop there, and we're going to go ahead and do another video in a minute we'll do the IVT.